Okay, while we are thinking about planes and their intersection, let's connect all this really back to the stuff we did in the first week of class. Okay, so I want to find the intersection of these two planes. Now, this is not necessary what I'm about to do here, but it's useful to think about. My normal vector for this first plane is 1, 2, 1, and my normal vector for this second plane is 1, 3, 4. Those normal vectors are not scalar multiples. So N1 is not parallel to N2 because not scalar multiples. So if we think about it, we talked about this in the last question, if two planes are not parallel, so they don't have the same slope, then hands down, they're gonna come and intersect each other. Two planes, they don't have the same slope, eventually they will intersect each other, they will touch. So we know these planes intersect. They also clearly aren't the same plane, so they're not the same plane. Because again, their normal vectors aren't parallel. So they intersect in a line. I know that before I even start this question, right? I can look at those normal vectors, they're not parallel, which means that the planes aren't parallel, the planes don't have the same slope, so they're not parallel to each other, which means they intersect, and they're not gonna intersect in a plane because they're not the same plane. So then how do I find the intersection of these two planes? That is the same thing as solving the system of equations of these two planes. So in other words, we can take these two planes and stick them in a matrix. And just do some row operations. So I'm going to do row 2 minus row 1. 1, 0, 2, 1, 6, 3 minus 2 is 1, 4 minus 1 is 3, 12 minus 6 is 6. And then I will do row 1 minus 2, row 2, to give me 1, 0, 0, 1. 1 minus 6 is negative 5. 6 minus 12 is negative 6, and then that's 3, 6. So I have two pivots here in my answer, which means I have one free variable. We know one free variable means intersection in a line. Now I remind you, an augmented matrix in RREF is not a solution. This is not the solution. We have to actually write the solution. So when we're writing the solution, we have our variables for each column, x, y, z. Our free variable, the first thing we want to do is assign it a parameter. And then my x will be equal to negative 6 plus 5t. My y will be equal to 6 minus 3t. And my z will be equal to t. This right here is the parametric solution of the line of intersection. So in other words, the planes intersect in this line. But we have been working with vectors here. So we saw at the beginning of the semester that this is another way that I can express a line. We've seen that if I have a general form of the line, that's going to have the two variables, the x and y. We also said that we can only use to describe a line in R2. In other words, if I'm like on a plane, if I'm in 2 dimensions, I can describe that line. If I'm in R3, so I have 3 variables and I have my line floating around a room, as opposed to like stuck on a piece of paper, then I'm gonna have to use some other form to express that line. This is one of those forms, this parametric form. But we've been working with vectors. So another way that I could write this line would be to take each of these things and stick them in vectors so that xyz becomes a vector. My constant becomes a vector. So x equals negative 6 plus 5t. The constant there is negative 6. y equals 6 minus 3t. The constant there is 6. Z equals t. There is no constant, so that makes the constant 0. Plus t times, well, now this is going to be my t vector. What am I multiplying by t and my x? 5. With my y, -3, and with my z, 1. So this vector equation, this is what's called a vector equation, and it's a vector equation that represents the exact same line. So vector equation of the same line. So in other words, I can take these parametric equations that we've been using and see how they can represent a line or a plane. And that's what we'll be doing next. So that's all. The solution, guys, is the x, y, z. It's not that matrix. This is my solution. All right, that's all.